Right. Welcome back, everyone. Let's get started. So in the last class, we discussed the concept of negative capacitance and negative capacitance transistor. Basically, this is another form of ferroelectric memory that we are going for, because this negative capacitance is observed or can be observed in a ferroelectric material, experimentally. And using that ferroelectric negative capacitance, we could come up with a transistor that gives you steeper switching. And using that steeper switching characteristics, we can eventually design or redesign, I should say, SRAMs. And we discussed what happens to the SRAM. Why is it unique? It's not just a drop-in replacement. Oh, you have a better transistor, so you have some incremental improvement in the SRAM characteristics. It basically uses a very different principle of completely redesigning the butterfly curve for the SRAMs, right? I hope you guys remember that. Apparently, using the negative differential resistance observed in this transistor, we were able to get hysteretic voltage transfer characteristics. Get used to these terms. BTC is just for one inverter. But then when you have back-to-back inverter connected in a SRAM cell, like here, you have to care about the butterfly curve. And because of the hysteresis BTC, the butterfly curve becomes more complicated, and only it turns out that we have both lobes amplified in size, apparently, and both of them are valid, because one of the lobes that are amplified is used for the forward sweep when you increase the voltage. The other lobe, which is amplified as well, is used in the reverse sweep. Okay, and that's why you can amplify both lobes, which is practically impossible for a conventional CMOS based approach, because when you make one of the lobes bigger, the other one gets smaller, right? So that was the signature of having multiple stable state in the load line analysis. And I told you that this is a very complicated concept to grasp, and I completely appreciate that. I still wanted to touch upon it because it's like so cutting edge. Okay, as you see, 2021, like not even 5 years ago. So I still wanted to touch upon it, but in case you don't feel comfortable getting deeper into this concept at this point, it's okay. I'm not gonna test you on this in your midterm or other quizzes. Okay, but I want you to at least give it a thought, and if you have questions, I'm more than happy to answer this. Okay, all right, so getting back to something that you should definitely care about, no exception here, which is a more serious form of ferroelectric memory that is currently being used. Many industry folks are actually going after this memory direction, which is just conventional non-volatile FEFET based memory. So the previous one was also FEFET based memory, ferroelectric FET based memory, but nobody calls it FEFET. Everybody calls it NC-FET, negative capacitance FET, because you're using the negative capacitance of the ferroelectric to get whatever you're trying to get. So the previous concept was NC-FET based memory. But now we are moving forward to FEFET based memory, where the ferroelectric property is crucial. We don't care about negative capacitance, and in fact, we don't get negative capacitance here. Remember, the same ferroelectric material could exhibit negative capacitance or not based on some co-design with the other dielectric. And I'm not getting into the detail of any of this willingly. Okay, but if you want to push me into a tangent, I'm happy to do that any day. Especially, I do recommend, please use my office hours, because I want to talk about this stuff. But if you don't ask me, then I don't get to talk about them, right? If you're interested, come to my office and I will talk about it. Okay, but getting back to the conventional structure of a ferroelectric FET-based transistor, have we seen this before in NC-FET? Didn't we? So basically, you have the exact same structure. What changes is the thickness of the ferroelectric. Apparently, by tuning the thickness, you can try to harness the negative capacitance nature or just the conventional FEFET nature. Yeah. So the structure of the transistor doesn't change at all. The only thing that changes is the thickness of the ferroelectric, typically. Are you guys all good with that? All right. To be more exact, it's not just the thickness of the ferroelectric, it's the relative thickness of the ferroelectric and the dielectric. So there is another dielectric material underneath. So if you have PZT as ferroelectric, underneath there could be hafnium oxide as well. So you always have a conventional oxide, and then on top of it, you have ferroelectric oxide in the transistor. So the relative thickness matters. But we could always decide to just keep the dielectric thickness constant and only tune the ferroelectric thickness. That works too. Okay. Regardless, you end up with this polarization versus voltage characteristics. Have you seen this before? Have you seen this? Okay. Where have you seen this? Like in the very first slide, we started with this PV loop actually, right? Okay. So there are different kinds of ferroelectric, by the way. Some will show you PV loop like this. Some will show you PV loop that are similar to this, and so on. There is a spectrum out there. Okay. So this is a different kind of ferroelectric material as you see, but it's still PV loop. Why do we have so many curves? Let's zoom in and see the legend. This is taken from a reference, so it's a little bit blurred, but I hope you can still see it. Notice what changes here. The thickness of the ferroelectric, right? As you make the ferroelectric thicker, the polarization hysteresis becomes wider. You see that? Okay, all right. Actually, we'll go the other direction. We want everything to be thinner. So instead of going towards the black curve, we were heading towards the red curve. We are trying to make this as small as possible. But why stop at 6 nanometer? Why not try to go for 3 and 4 or smaller than that, right? And I will explain that here. Notice here, this is for a ferroelectric capacitor. Ferroelectric capacitor is nothing but a standalone ferroelectric material, okay? But the diagram that you see, which looks kind of similar to the PV loop that we observed, this is for ferroelectric transistor. So apparently in a ferroelectric transistor, which has ferroelectric material, let me change the color, which has ferroelectric material here. So maybe this is ferroelectric, but you also have a dielectric underneath, okay? There is a combination. So together, the ferroelectric property could still prevail, or ferroelectric property could completely be, disrupted as well. Depends on the thickness of the ferroelectric. And let's see what happens there. When you have 8 nanometer thick ferroelectric, you still have hysteresis, but the hysteresis reduces compared to the standalone capacitor. Do you see that? Just compare them side by side. The black line with the black line on the left. So this is standalone capacitor. And you have a wider ferroelectric thickness, wider ferroelectric polarization loop for 8 nanometer thickness. But when you make it into a transistor and use the same thickness of the ferroelectric, the hysteresis loop reduces. Do you observe that? Okay. And keep doing for the rest of the thickness that we have, 7 or 6. At some point, for 6 nanometer thickness, notice the ferroelectric polarization or hysteresis it has kind of gone away. Are we good? Okay. What does that mean? I'll tell you what that means. But remember, we are looking for the polarization versus voltage characteristics to be hysteretic, okay, even in the transistor. So that means you cannot use 6 nanometer. You have to use minimum 7 nanometer, or if possible, more. Are you guys all good with me? Okay. Just take a look at this device characteristics and tell me why I don't want to go from 7 nanometer to 15 nanometer. I want to use as small of a thickness as possible. Why? Why is that? Just look at this device and tell me. Thank you. Yes, so you do remember. Thank you. I hope the rest of you also remember. We discussed this before, right? When you make the ferroelectric thicker, maybe this layer thicker, it's not just going higher up, it's also being wider in this direction because of this being a FinFET. And same applies to the other one. And then you have to maintain pitch. You have to spread them further out. So, and in doing so, you basically increase the overall width of the transistor. So that means we want to make things, the ferroelectric thickness smaller, but then there is a lower limit. You cannot go beyond 7. Yes. Yeah. Great question. So it is basically, there are some hysteresis if you zoom in and whatnot, but we cannot use them practically. And I'll show you how we use them in a second. Then you will realize. So basically, the wider the hysteresis, the easier it is to use. Okay. So obviously, I love 8 nanometer. But what is the problem with 8 nanometer? The problem is you have to make them wider. So there has to be a compromise or optimization involved. So that's why we decided to go for, say, 7 nanometer. And don't take these numbers to be so serious. This is for one ferroelectric material. The moment you get to a different ferroelectric material, these numbers will change. Okay. All right. But these trends will remain. So you do care about the trend. Apparently, we want the ferroelectric thickness to be as small as possible. But if you go too small, then you kind of diminish the ferroelectric hysteresis. And by the way, if you go to 2 nanometer or even 4 nanometer, this will be completely flat, just one line. So this ferroelectric property is gone. Okay, it is overwhelmed by the dielectric property. Okay, and now I know it's a little bit difficult to track because these are all taken from real references. I wanted to have real data here, but then to explain, I'll draw. But then it means that you have to pay attention, right? Okay, let's do it. If you have a transistor like this, let me draw the ID versus VGS characteristics of a transistor. Okay, ID versus VGS. It basically looks like this. So you have a threshold voltage, V threshold, and above the threshold voltage, the transistor turns on. All good? In log scale, we discussed this before. In log scale, basically, if you plot this in log 10 ID versus VGS, wherever you have the threshold voltage, up to that point, you have a rapid rise, and then it stabilizes, almost saturates. Okay, this is how it looks like. So get used to this, like both type of representations. Now, where I'm going with it is, if somehow you manage to tune the threshold voltage of the transistor, if you increase it or decrease it, what happens to this curve? Let's say you increase the threshold voltage. So it's as if you basically just shift the curve horizontally to the right or left. Okay, so basically you change this curve and shift it to right. So this is V threshold 2, which is greater than V threshold 1. All right. And similarly, if you reduce the threshold voltage, it moves to the other direction. And so on. So if you could somehow change the threshold voltage of a transistor, the IDVG property will shift left or right. Are you all good? Okay. That's one point. Now, how can I change the threshold voltage? There are many ways. One is to use body bias. And we discussed that in the SM lecture. Remember? You can body bias the transistor to do so. Another approach would be, if depending on the fixed charge that appears at the gate, who determines the threshold voltage? Many factors work together. But one of the factors would be how much gate charge you have. How much charge do you have at the gate? Okay. So if you somehow provide some fixed positive gate charge, it basically shifts the threshold voltage. And if positive charge shifts it one way, negative charge will definitely shift it the other way, as you can imagine. Am I making sense? If by using positive charge, you increase the threshold voltage, negative charge will decrease the threshold voltage, and vice versa. Are we all good? Okay. All right. So keeping that in mind, let's talk about ferroelectric transistor. So you have ferroelectric added to the gate. This is ferroelectric transistor. And ferroelectric material could be set in positive polarization or negative polarization. So imagine when you have positive polarization, you have a certain threshold voltage. When you have negative polarization, you have a different threshold voltage. Does that make sense? So basically the same transistor, you could change the threshold voltage of the transistor by programming the ferroelectric in different polarization states, either positive or negative. So the transistor shows you two different threshold voltages. Is that clear enough for us? Okay, this is the basic principle. And let me show you. So if I somehow apply a voltage, you have to notice when I draw, okay? Let me change the color. If I somehow apply a voltage of this much, say this is my read voltage, to the transistor, we apply that much gate voltage to the transistor. Depending on whether or not it was storing positive polarization or negative polarization, you will either have low current or high current. Does that make sense? So when you apply a voltage, you get low current, oh, it was storing so-and-so polarization. But if you get high current, opposite polarization. And polarization could represent 1 and 0. And that's how you read. So I'm giving you the overall principle of operation for FE-fed based memory. So do you see that FE-feds can somehow, in an interesting way, use the polarization and transfer it into the current of the transistor? Okay, I'll tell you the beauty of this approach. I hope you guys remember how we used to read ferroelectric capacitor or FE cap based memory. What was the biggest issue with that? Can anybody tell me? Thank you. Destructive. But is it just you? Do you guys also remember, folks? Thank you for responding. I really appreciate it. But you guys should also speak up. Do you guys remember that or no? That was the biggest challenge. So we were trying to go through, while trying to read, we basically had to go through this route for at least one of the situations. And for the other one, we didn't switch. For one of them, we switched. So that means every time we read, we had to write back. So that was the biggest challenge for FE cap based memory. And let me show you why this approach that I just explained, which merges ferroelectric property with the transistor, helps. Let me show you. I'll make a really big plot. Okay. So how do you program the ferroelectric material? Here is how. You apply gate voltage and there is source terminal, which could be set to ground, or you could have basically a voltage source between gate and source. Okay. So by applying positive voltage to the gate, you program the ferroelectric material in positive polarization. Or by applying negative voltage to the gate, or negative VGS basically, you don't have to use negative voltage. You can always use VDD here and ground to the other side, or VDD here and ground to the gate terminal to achieve what you're trying to achieve, right? Positive polarization and negative polarization. Okay, so now notice this is the path that you use to program the ferroelectric material. Let me change the color here. This is the path from gate to source. It got really messy. And this is the path that you use to program the ferroelectric, gate to source every time. Now, when you read, here is how you read. You apply a voltage, like I just told you. You apply a voltage, say V read voltage, which is a drain voltage here, and that leads to a current, read current through the transistor. Notice the current is flowing through the transistor. It's not doing anything to the capacitor because it's in the gate step. It's not in the transistor channel. If you see a conventional MOSFET, source and drain, this is where your current flows through. But your ferroelectric is sitting here. This is your ferroelectric, not in the path of the current. It's completely separated, okay? So this current doesn't disturb the ferroelectric in any way. You can get a read current, which is high, as we just discussed, right? Corresponding to one kind of polarization, or a read current that is low, depending on whether this ferroelectric was programmed in positive polarization or negative polarization. For one of them, you had more current, other one, you have less current. So by using a constant applied voltage and sensing whether the current is higher or lower, you read what was being stored in the ferroelectric material. So what is this type of situation called? I mean, we saw this before. This is something that we really like, and I told you a couple of times before. Yes. Okay. Anyone wants to respond? Can you make a comment about this memory device? It has separate what? Separate read-write path. Do you guys all agree with it? So this is the write path. This is the read path, which makes it so easy for us. There are two reasons why we like separate read-write path. Write doesn't disturb read. Read doesn't disturb write. So there are no chances of accidental disturb, which is the first benefit. The second one is, since they're independent, you could optimize them without hurting the other. When they're coupled together, typically when you try to improve read, write suffers, and vice versa. But when they're decoupled like this, that's a tremendous advantage. And you're getting separate read-write path for free. Can anybody tell me which other memory technology had separate read-write path? Which one? STT or SRAM, you mean SRAM? No, SRAM has same read-write path. Okay, but there are some flavors of SRAM. You're right, actually. Remember, we talked about 80, 10T, 70, right? There are other T SRAM, not 60, not the standard one. So we had to use additional transistors to achieve separate read-write path. Okay, or which other in a recent discussion? Yes, spintronic. Remember SOTMRAM, spin orbit torque. We had one path that uses heavy metal to write and STT to read. Just compare that with this simplicity, right? Just one transistor, super simple. You use the gate stack to write, you use the drain to source to read. So this, is it, I mean, does it appear to be simpler than the STT or SOTMRAM or not? That's why people love it. It's easy to fabricate. You definitely remember how complicated the magnetic tunnel junction stack was, like 10, 12 different layers of materials. But here, just ferroelectric. And apparently, what supercharged interest in ferroelectricity-based memory, literally supercharged. And it happened not too long ago, basically in the last decade, after 2010, when, and remember this topic, and oftentimes if you interview for memory companies, they will ask you, hey, do you know about ferroelectric? Okay, why do you think we are suddenly so interested in it? What led to this? There is a point that people can basically refer to. Discovery of ferroelectricity in hafnium oxide. Why is that? Why is that? Can anybody guess? That's a good point. Yes, PZT was toxic. We love, but there are other ferroelectrics. Okay, aluminum, scandium nitride, barium titanate that are not toxic either. So that's not the main reason why we are so excited about it. Okay, do you guys know which oxide we use in our modern day transistors? MOS, metal oxide semiconductor. So we must be using some oxide, right? Which oxide do we use? Silicon dioxide was something that we used to use, okay, until 2000, like early 2000s. And then we switched over to something. Remember, the modern day transistor technology is called HKMG. I'll explain what that means. Yes. Is aluminum oxide? Well, not really. That is one specialized oxide that in some devices we use for some specific reasons, but it's not prevalent everywhere. Okay, there is one main candidate, and you should know this, by the way. Being a computer engineering student about to graduate, okay, so you definitely should know this. I mean, obviously, that's why I'm here to teach you. If somebody asks, hey, what type of transistor technologies we are using? We are all using HKMG. For the last 10, 15 years, we have been using HKMG. What does it stand for? Can anybody tell me? High K, what does MG stand for? Metal gate, remember? So we used to use polysilicon gate at some point, then we switched over to metal gate. All of these are linked together, but these are device level stuff. I'm not getting into this. But HKMG, what does high K represent? What does high K represent? It's a dielectric constant. So there has to be a dielectric material. What is the dielectric constant for silicon oxide? It's 3.9. We use an oxide which has about 24. So 22 to 24, depending on how you make it. That's hafnium oxide. Okay? So we have been using hafnium oxide for a while. And somebody discovered a technique to make hafnium oxide a ferroelectric. So folks, it's one thing to just draw a schematic and structure and show you, hey, we need like a sandwich. We need silicon oxide on top of it. We need PZT on top of it. We need aluminum. We need this and that. It's something else. How do you know that when you make a material on top of each other, say silicon oxide, and then on top of it you have PZT, blah, blah, blah. How do you know they will stay? Why would they stay? I mean, when you try to put a material on top of another, will they always stick? No, they might slide, right? There are mechanical stabilities that we often overlook. We take it for granted that they will just stick together. And we are using 3M glues or something, right? No, there is no way for us to make sure that these materials will stick on top of each other. The only way we should, to do so would be to have a lattice matching or some sort of lattice interaction that keeps them in place. Okay, so if I just come up with an idea that, hey, this is a great device idea, we need PZT on top of silicon oxide, blah, 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 blah. That doesn't mean that you have absolute guarantee that this will be mechanically stable. You guys all with me so far? Okay. So, but what if I told you that you have hafnium oxide that you already use? All I have to do is when we fabricate hafnium oxide, I'll have to dope it with zirconium oxide. So this is a doping. You guys must have heard about doping, right? P-type doping, N-type doping, right? So basically, when you introduce an impurity in a material, that's doping. So hafnium oxide was pure. You're introducing some additional random oxide called zirconium oxide there. And what you get is HZO, hafnium zirconium oxide. And that becomes a ferroelectric. And so people discovered a technique to make hafnium oxide ferroelectric. Now, you already have hafnium oxide there in the device. You just make a top layer. Instead of hafnium oxide, you can make it hafnium zirconium oxide. And there you go. You have a ferroelectric transistor. The super elegant fabrication methodology. That's why people are so excited. Does that make sense, folks? Okay. Everybody loves, especially industry loves simplicity. Like if it is easy to make, we will go for it. There are less things that can break. Why do you think, one of the selling points about EVs or likes of Teslas and others is that there are less parts to worry about. If you go for Mercedes-Benz or BMW, there's so many parts that could fail. So that's why it's risky. We talk about reliability, right? Less parts, less concern of breaking things. Similar to that, when you have less layers of materials to, worry about during fabrication, it's more reliable fabrication in general, okay? All right, so getting back to this point, there are many good things about FFET-based memory, separate read-write path, and especially if you are going for hafnium zirconium oxide-based FFET, super simple fabrication. That you don't have to change your tools. That was the deal maker for industries. We don't have to buy a new tools. We could just make, I don't know. It's kind of like having the same coffee maker, but using it to make other drinks as well, right? You can make Coca-Cola with my coffee maker. Sure. Okay, I'll take it. Similar to that. So let me get back to this slide, which we started talking with. We discussed the ferroelectric transistor and ferroelectric capacitor and the hysteresis that you get in both of them. And let me show you, I just drew this separately as a cartoon, but now we are going to look at some real data. Are you guys ready for it? Real data is always, difficult to look at because they don't want to explain anything. They're just speaking to other experts. They think that the other guy is also already an expert, right? So we are trying to be an expert here. So that means you have to pay attention, okay? Let's see. Why do you think there are 3 curves? What does the legend tell you? 3 thicknesses. I already told you one of them don't work. So don't go for, let's not look at 6 nanometer. Let's just look at 7 and 8 nanometer because both of them work, okay? Notice if you apply, this is what? ID versus VGS characteristics. Did I draw the ID versus VGS characteristics when I explained that? I drew it in linear scale, but I also showed you the logarithmic scale, did I? So this is a log scale plot. Sorry, this is also linear scale plot. Good, fine. This is also linear scale plot. Fine. What you have here is, instead of having 2 lines separately drawn like I did before, so we are looking at what happens when they merge eventually. What I didn't show you is, sorry, going back and forth here. What I didn't show you is after you have shifted threshold voltage like this, it's possible that they will basically merge together. It's possible, okay? But you don't care about that region. You are only dealing with this region where you have a difference in current, okay? So basically, let me zoom in again. If you select a voltage like 0.1 volt here, for that voltage, you get really low current for one situation, and you get really high current for the opposite kind of polarization. Does that make sense to you guys or no? Okay. Okay, so do you think the black one is better or the blue one is better? The blue one is better. Why? Because it has lower thickness. You are right. But there are other challenges. Simply because I love lower thicknesses doesn't mean I can go for it. Okay. Remember, when I say I can apply 0.1 volt, remember, nothing is guaranteed. It's never going to be 0.1. It's going to be 0.12, 0.14, 0.9, 0.8, 0.75. There will be a fluctuation everywhere, right? Nothing is guaranteed unless you go cryogenic, like super, super cold. Then you don't have to worry about thermal noise and whatnot. But apparently, you get thermal noise voltage for free. Any voltage that you apply, noise will be added or subtracted from it. That means if you are dealing with such a small window, maybe I was shooting for this voltage point, but then I'll go over. What happens when you go over? Notice immediately here, I know it's messy, but please pay attention when I draw, then it will be easy for you to understand, okay? Notice, I was trying to go for this point, A, but for variation, I ended up with B, which is not too far, but what happened is, now B takes me to this region where there is no difference, right? It's beyond the hysteresis. So if the hysteresis is too narrow, it's easy for us to miss during read. So read failure. You misread high current. But apparently both of them will give you high current. You don't know, right? So the black line, black hysteresis is wider. So if you choose one point, there is a chance that even with fluctuation, you'll be able to sense. So that's why hysteresis, too much hysteresis is bad, too less is also bad. So there has to be an optimization. All right. Okay. Now everything is easier said than done, right? As you know. Yes. Let me show you. Yeah. That's a great point. Okay. That's a great point. So let me rephrase the question for you so that you appreciate the question. And that will help you understand the beauty of non-volatile memory. Are you willing to pay attention? Okay. First point is, notice, so there are two curves, right? One is this one and the other one is this one. Both are green here, but you see one of them, look at 0 volt. Look at 0 volt, right? 0 volt means it's off. Even when it is off, one of them has a really high current compared to the other one. That means it will be leaking like crazy. Does that make sense, folks? And did I tell you that leakage is a problem? Everywhere. DRAM, SRAM specifically, because the SRAM that you are using, others are leaking. And they're just taking up your battery voltage, battery current, right? So why cannot we get around the leakage problem? If I have a leaky transistor like this in SRAM, I'm done. Why? Can anybody tell me? Very quickly, there is a SRAM figure here. It will drain, yes. The reason why SRAM has no respite from this problem is because, to hold on to the data, you need what? I'm pointing to it. You need VDD. If you remove VDD, these cross-coupled inverters will no longer work, and you lose everything. You lose everything. There is no data left. So you have to keep applying VDD. Remember, when I draw ID versus VGS characteristics, and I tell you that this is the off current, this is the on current, this is off, this is on. There is one more information hidden in this ID VGS characteristic. What is that? Who can tell me? What? The VDS. Thank you. VDS. What is the VDS? There has to be a non-zero VDS. If you apply VDS equals 0, then what? Then there is no off current. There is no current at all. It's absolutely 0. But only when, even if it is a small, tiny 0.1 volt VDS, you have off current. Okay? So you have to have VDS. Now notice, in SRAM, when you apply VDD, that provides VDS to the transistor. That means the transistors leak. There is an off current. But if I could completely get rid of VDD, if my SRAM could still remember what was stored, then there is no problem. I don't care if it is a leaky transistor. I don't care, right? Okay, so now getting back to this point, will ferroelectric remember how it was programmed even when I remove the voltage? What do you think? Yes, it's a non-volatile memory. So once you program it to positive polarization, even when you remove the voltage completely, it will remember that I was positive before. And then when you restart, it will start from positive polarization and so on. So that means when you're not reading or writing, all the other cells could have. So this data doesn't show you one thing, the VDS. There is a VDS. Only when you apply VDS, you get this. But for all the other cells that you're not accessing, you set VDS equal 0. So when you say 0, done. So that was a great question. And that's the reason why non-volatile memories survive. No matter how leaky the transistors are, they survive. But volatiles cannot. Are you all good? Okay. So excellent question, by the way. I'm really glad. All right, next, moving to the next point. Everything is easier said than done, right? I told you that, hey, this is a ferroelectric transistor. This is how you write. This is how you read, blah, blah, blah. But there has to be a controller, as you can imagine. And we discussed that many times. Just the transistor itself, FET itself, cannot work. Did we use this argument for MTJ? Oh, just take an MTJ. Take an MTJ like this and just run some metal lines here and there, apply voltages and write into it, read from it, blah, blah, blah. What was the issue, folks? Can you remember? The issue is not about the one that is being accessed. It's about the one that are not being accessed. So the problem is, since you share this interconnect lines, if you just use the interconnect, you'll end up programming the others or destroying the others. So to avoid that, we need what? Selectors or access devices that are transistors. So apparently, you need an extra transistor for FET as well. And this is, I'll start with this and I'll show you the array in the next slide, okay? But I'll start with this. This is the access transistor that helps us control the FET. Still with me? All right, FET, sure. So you write into the FET or read from the FET this way. All right, so this explains how you write. So you apply a voltage pulse through this transistor to the gate, and that's how you write. And how do you read? You read through this channel, which I've just explained. Let's move to the array level scenario. This is how the array looks like. It's not unusual, but it's a little bit of a newer flavor. Why do you think? Because all the other memories you have seen, like STT-MRAM, for example, or DRAM, they had a transistor, and in series with the transistor, you had something, either a capacitor or a resistor or something. It was always 1T 1R or 1C 1R or something. There was 1T and then others, right? But here it's, how can I put it? I should put it at 2T. There are two transistors. Okay, some people prefer putting it as 1T 1 FET, because the other one is not just a transistor, it's a FET. So in some references, you will get 1T 1 FET. Somewhere they will just go with 2T. I guess all good so far. The other uniqueness here is that for all the other memories, the memory element, for DRAM it was capacitor, for STT-MRAM it was MTJ. They were, and you will go through others, PCM, resistive RAM memristors, they will all be similar to this format, 1T 1R. So you'll see them. Basically, they were all connected to the drain or the source of the transistor. Okay, here it's a little bit unique because it is directly feeding into, I mean, the access transistor is still using its drain or source, but it is feeding into the gate of another transistor. Okay, that's the other reason why the array looks unique. But other than that, there is no other uniqueness here. Okay, so you still need a word line. You activate this transistors using the word line when you read or write, right? And then you still have bit line and source line. You have to provide voltages to these two sides of the transistor, right? So that means you need bit line and source line as well. Yes. It's a great question. So typically the write asymmetry is very, very minimal. They can, especially because I haven't showed you those results. We have been looking at ideal ferroelectric material mostly. So uniform EC plus EC minus EC, coercive voltage or coercive field. But there are situations where there could be skewness in the ferroelectric. It could be plus EC1 minus EC2. Like there could be difference there. If that's the case, then yes, for sure. And there are other reasons why, because of the interaction between dielectric and ferroelectric, some depolarization effect occurs, and that leads to asymmetry. But these are getting into real weeds in the FFET. But it's a good question, but it's not really that much of a concern, honestly. By using intelligent fabrication method, we could minimize those effects. We could minimize those asymmetry. All right. Now, just to touch upon the layout, again, these are taken from advanced references, by the way. And I mean, I don't know how calibrated you are. The graduate students, how many of you are graduate students? Can you raise your hands? Many of you. I highly recommend familiarize yourself with the top venues in your major. Like if you're a computer engineer, what are the top conferences for computer engineering? What are the top journals for computer engineering, right? For example, DEC. This is basically the top. I mean, arguably, everybody wants to call themselves top, but it's kind of agreed upon that they're basically the top conference in chip design domain. Okay, so these are from really top venues, as you see, and not too long ago. 2016 is basically nothing. These are baby step compared to SRAM, 1960s, right? Or DRAM, 1970s and whatnot. Okay, so this is an FFET array, and they're comparing it with FE cap array. Why? Ferroelectric capacitor-based memory was proposed decades ago. You know that? Like basically decade ago than FFET. FFET-based memory is a recent development, where instead of using the capacitor and using the destructive read, we are basically using the transistors channel to read out. And doing so, you need two transistors instead of one. FE cap required just a transistor and a ferroelectric capacitor. So it was 1C, 1T, 1C. So it feels like, oh, that's great. But then you have like destructive read and whatnot. But they still have to be fair. When you come up with an idea, you have to show all sides. And I want you to understand, I'm not getting into the details of how you design this, blah, 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 because most of these are FinFET architecture. But I want to show you that this is what you need to report. When you come up with a new memory array or new memory technology, you have to compare it against its immediate competitor. Okay, so take a look at this. In terms of area, what does F represent? Remember we discussed 4F squared, right? F is the half of minimum feature size. These are real data. So basically they represented that here. This direction would be 6.5F, and here this would be 7.25F and whatnot. Okay, so this is the area. And on the other hand, for this one, you can clearly see the area will be bigger than the other one. Area will be bigger. Okay, all right. So you immediately see the catch here. You are spending more area, but what are you getting? Separate read path, no destructive read, blah, blah, blah. You're gaining some, you're losing some. Did I tell you there is no free lunch in engineering, right? You keep seeing that actually over and over again. Nothing is free. You get something, you lose something else. Okay, and by the way, so this is one cell. This is the other cell. This is the other cell. This is the other cell. So basically, that's the beauty of memory design. Once you design one cell really well, like literally this one, just take copy, paste. To the right, row, column, row, and column. You see that? Even you don't even copy paste anymore. There are codes that you write, like, okay, repeat it 256 times across row. Just put the number 256. It'll make, right? I teach it in 651. I don't know if you have taken ECE 651. Typically, Professor Rose and I, we used to rotate on this course. There we teach skill coding. This is a type of language, like coding language. And one of the homework is designing an SRAM layout from scratch. So you go through all those transistors, make connections, and make this cell, for example. Imagine this is an SRAM. And the next time, you have to make an array. And people freak out. Oh my goodness, it took me like several hours to make an SRAM cell. But now I have to make 32 of them? No. All you have to do is just put 32 in the code. And that was the beauty. That tells you how EDA works. Electronic design automation works in electronics. Basically, nobody does things manually anymore. So you simply cannot afford to do so. So for memory, all the manual work, all the technical rigor goes into designing this cell, simple cell. So when you see this 1T1R cell being emphasized so many. Where's the circuit? This is the circuit, basically, right? Just take it, copy it over, you get an array. So going from device to array is like this for memory design, for most part. Device to array. I didn't say peripheral. Okay, peripheral is a very different beast. We'll talk about that. All right. We have a few minutes left, but these are pretty quick slides, just data to present. Ready for it? All right. What are the challenges? Other challenges. We have seen some challenges. Some other challenges would be depolarization. I keep using the term depolarization. This is basically, so when you polarize a ferroelectric, make it positive polarization or negative polarization and let it go, it's not going to remain there forever. There is a physical process through which it will gradually relax and lose its charge. Unlike a regular capacitor that loses charge immediately, almost in milliseconds, it will be like several years, right? But it will still depolarize, okay? And depolarization, as you see, this is the extent of depolarization field. The lower the thickness is, this is lowering thickness. The lower the thickness is, the higher the depolarization effect would be. So this is the depolarization field. And notice this is negative. That means just treat it like opposite. Take the absolute value and I guess I made you confused. What I meant by that is this is -2, -4, -6 doesn't mean anything. Just consider them to be 2, 4, and 6. Consider the absolute value. So the deeper you go, the higher the value is. Okay? So you are getting stronger depolarization as you reduce the thickness. So that means you cannot reduce the thickness beyond a certain limit. Let's see. PZT doesn't allow you to reduce the thickness beyond a certain number. Did I tell you PZT requires higher thickness? Beyond lead poisoning and whatnot, we also worry about higher thickness. Because what? Because if you go beyond that thickness, it starts depolarizing itself. And how about hafnium oxide? Great. That's our hero. So it allows us to further reduce the thickness. Maybe it can take better heat than PZT. Easier fabrication. And what else do you need? Right? Okay. So there are other materials, and we do these studies for aluminum, scandium nitrate is another one, which is good. One other thing to keep in mind is the dielectric constant of ferroelectric material is related to its coercive field. So you typically have to worry about the capacitance that this ferroelectric material is bringing. I'm deliberately not getting into this degree of detail, but remember, dielectric constant determines the capacitance. Ferroelectric material is also a capacitor, okay? It has capacitive coupling with the dielectric underneath, okay? And that has some performance implications, especially in terms of speed, switching speed, okay? It's not the biggest of the worries, but we do care about reducing the coercive field as much as possible. And if possible, changing the dielectric constant to the direction we want. We want to increase it or decrease it at will. But apparently, that's not possible. In nature, you get a trend. Apparently, the lower the dielectric constant is, the higher the coercive field is. Typically, that's experimentally observed. So you're kind of stuck with this design restriction. So we're done almost. So again, I have a few slides. Maybe let me do one thing. Rather than rushing through it, let's finish up these 2 slides in the next class and start fresh with the next lecture. Okay. So we'll talk about this limitation, and this chart will come later on. Thank you, everyone.